Okay, end of chapter problems. Starting with number 15. It says, calculate the pH of the 0.2 molar ammonia, 0.2 molar ammonium chloride buffer. What is the pH of the buffer after the addition of 10 mils of HCl to 65 of the buffer? Okay. It's a buffer problem, so its pH is equal to pKa plus the log of the concentration of the base over the concentration of the acid. The base is going to be the NH3, and the acid's going to be the NH4Cl. And I know that because the acid always has one extra hydrogen than the base. Okay? A pKa is a negative log of a Ka. But when I look at my Ka table, I won't find ammonium ion on there because it's not an acid. Ammonia is a weak base, and ammonium is the conjugate acid of it. So what I'm going to have to do is I'm going to have to look up a Kb, figure out the Ka, and then take the negative log of it to get the pKa. Okay, so ammonia, Kb is 1.8 times 10 to the minus 5. So Kw divided by Kb is Ka. So Ka is 5.6 times 10 to the minus 10. pKa is 9.26. Oh, base is 0.2 in the problem. Acid's 0.2. 0.2 divided by 0.2 is 1. The log of 1 is 0. So the pH is equal to 9.26. Is that right?
It says 9.25 on here. But
Okay. It's the rounding right here.
I
So
did get that same thing as you did.
Okay, yeah. When I plug in the negative log of, like really right here, I didn't get 5.6 times 10 to the minus 10. I really, in my calculator, got 5.5555. So I actually took the negative log of that, which is 9.26. If I put in it rounded, it's 9.25. So we're right. Yeah? Okay. And so the next part, what's the pH of the buffer after the addition of, okay, the base is on top, and we're going to add acid to it. So we're going to subtract the moles of acid here and add it here. We're going to have to convert everything to moles too, right? We're going to have to take the 0.2 molar times 0.065 of the buffer, et cetera, et cetera. Does that make sense?
Mm-hmm.
I'm asking y'all, and I hope it does, Chance, because I was going to leave it right there and let you figure the rest out. Yeah?
I think I got that one, yeah.
Okay, so I'm going to look at 63 now. Okay.
Awesome.
All right, so PBBR2, number 63, we're told that the KSP is 8.9 times 10 to the minus 6. Determine the molar solubility, okay, in pure water. So PBBR2, I hope that we can see that is a 4x cubed one. A part asks for the molar solubility in pure water. So that means I just need to do this and solve for x. For the molar solubility, I get 0.0131 molar.
I don't remember if I did
Okay,
that one.
that's okay. I keep looking at Bryce to tell me the answer, and I can always just look in the back of the book.
Right here.
What is this?
I can look right here. Yeah, that's what it says.
Okay. Like this. Okay. Then B part says in 0.2 molar potassium bromide. Okay, so we know that this KSP is equal to the concentration of the lead times the concentration of the bromide squared. And if we're putting it in 0.2 molar bromide, like for A part, it was just in water. But for B part, we've got a common ion there. We've already got bromide there. And so what that means, if I could show you with an ice table. That if we start with some of this, some of it's going to ionize, right? And this doesn't matter because that's a solid. We're going to make X lead and 2X of the bromide. But in A part, see, we had 0 lead and 0 bromide. But in B part, we have no lead and we're starting with 0.2 molar bromide because it's 0.2 molar. And so at equilibrium, we end up with this. We assume this is really small. So we plug in KSP, 8.9 times 10 to the minus 6 is equal to lead, which is X, times the bromide, which is 0.2 squared. And we solve for X.
Why would you, I have a question about that.
Uh-huh.
Why would you not multiply that by 2 as well?
Because it's coming from the bromide, from the KBr. And so when KBr ionizes, it's potassium and bromide. If I start with, I'm doing a little ice table, chicken scratch over here. If I start with 0.2 molar KBr,
Okay.
all of that ionizes. That
Yeah.
means I have 0.2 potassium and 0.2 of the bromide.
Okay.
That's where this 0.2 is coming from. It's not coming
Well-
from,
Well, I see where that's coming from, but I'm talking about the coefficient on the BR up there, how it's a 2. I thought, wouldn't you multiply your 0.2 times that and square it?
mm-mm.
Oh.
So you divide the base by itself? Yes.
Because the only place you use the coefficient is the change line.
No, that's
You need
right.
to log that in.
We don't use it on the initial line.
Yes.
And when,
Okay.
does that make sense?
Yes.
Okay.
Yes. Okay. Alright, so that would be 0.4.
So you divide that number by the total.
I get, yeah, 2.225 times 10 to the minus 4. And I checked it, it's right. For B. Then for C part, hang on. You're putting it in 0.20 molar lead to nitrate. Well, the common ion's the lead. And see, when this ionizes, it's going to make 0.2 molar of the lead and 0.4 molar of the nitrate. But the KSP, the common ion's the lead. So, our starting amount is 0.2 molar of the lead. When it ionizes, we make X lead and 2X of the bromide. So at equilibrium, we have 0.2 plus X and 2X. We assume this is really small. So, where is it? We'll say 8.9 times 10 to the minus 6 is equal to the lead times the 2X squared.
I was gonna forget to square that.
Oh, I punched something in wrong. Get that x is 3.3. Times 10 minus 3 molar. Yeah.
Right. I messed up somewhere though.
Okay.
And that gives you a number. and you have to
Okay, then 65.
of that. And then you
After
just-
working these, you might see how to do that because it's very similar. 65 is about barium sulfate and water. Barium sulfate's an x squared one. So for A part, you say, oh, I just closed my book. You say 1.1 times 10 to the minus 10, which is the KSP, is equal to x squared, and you solve for x. And for x, I get 1.05 times 10 to the minus 5, and that's molar. I lost my place. on my-
That's right.
Okay, thank you. And then when I put it in 1 molar sulfate, well, this was the barium times the sulfate. And then when it's in water, the barium is X and the sulfate is X. But when you're putting it in 1 molar sulfate, it's 1.1 times 10 minus 10 is equal to the barium, which is X, but the sulfate is now 1. And so X is equal to 1.1 times 10 minus 10. Yeah. And now I'm going to stop this and upload it.